So thanks. Thanks for the introduction. Just to a bit of location. So we are here in Geneva. I grew up here, but now I'm working in Yverdon-les-Bains, which is like 90 kilometers from here, in an institute of embedded and reconfigurable digital systems. And actually, in this institute, we are 8 professors and 20 people working on different projects, from the PCB design up to the FPGA and the embedded software. So we have the full team of playing with that and with the issue of checking that everyone is doing a great job in verifying that everything works well. So my first assumption is that you follow the previous talk. I guess that's all right for people here. And then maybe you would say, okay, it's written 76 slides, but there is a coffee pretty soon, so he's crazy or not? No, so I'll stop at 45. You will see why later on. All right. So if we start again with verification of digital systems, we have to answer 2 questions. Does it work? That's the first one. But then the second one is, are you sure it really works? And that's the real issue, usually. But actually, there are 3 more questions to this. It's really? Well, really, really sure? And no kidding? You're sure that really it works? And that's the real issue when doing verification, because it's very easy to develop a test bench. You design your VHDL design, you write a little test bench, and obviously you will be very confident that you did something very well with yourself, and you should agree with yourself, and that's part of the issue. So the idea is that really we have to assert that the design is very exactly what it was supposed to be with this specification, and the idea is to prove that it does. So we can do it by simulation. That's what people do usually, as we saw with the hands-on previously. Usually in simulation, that you write your test benches. You can do formal verification. That's what we'll be talking a bit more about this right here. And you can do the real test on the hardware. It's nice to end up with the real test at the end, but then the observability is not very good because it's hard to know what you have in every single register on your FPGA. Sure. So if we stay with simulation first, you have to design this test bench, and then you have to choose what kind of test or scenario you want to do. So usually you would go with directed test, so you really decide what you put as the input of the design. But then it's very hard to think about some corner cases, because that's where the evil is hidden, actually. And so usually we would suggest to do some random-based simulation. So System Verilog is quite good with randomization. Now you have UVVM as well, offering nice ways of doing this. And for me, the best way is to mix both approaches. So you have some directed tests, scenarios, and then some randomness, just to find things you wouldn't have think of as a designer. And so for the test bench, you would maybe start with a reference, maybe some VHDL, non-synthesizable, then your design. You would generate some stimuli, and then check that the output is correct, and then generate some errors if it fails. So that's kind of the basic test bench, much simpler than UVVM ones, for sure. But then usually, it's not like just a counter that you will verify. So you will have maybe a design where there is a bus on one side, maybe an AXE bus, and then that could be a memory controller. So on the other side, you have a memory outside of the system, and so you have to design all of these parts. So you have a more complex test bench. UVVM can solve that as well, but you need to dig a bit about in the BFM model you would have. And then another option would go to UVM, for instance, if you do System Verilog. And the UVM test bench would look like this. So you have the top, you have the design under verification, right on the bottom here. And on the top, you will have some test cases that would embed a test bench, that would embed a verification IP, that would embed agents, and an agent would be like a sequencer that would generate scenarios. a driver that would interact with the design, and a monitor, a collector to observe what's happening on the bus or on the input-output of the system. Then you could have different agents on this. And so it's a bit more complex for sure. So before going to formal, because we are here to share as well, as we saw the two previous days, if you want to play with UVM, one issue is to start, because it's kind of complex. So if you want to start with, there is a scoreboard as well, forgot that. If you want to start with, you can give it a try to go to systemverilog.ch. Over there, we have a software we developed like 10 years ago, where you have a wizard that helps you define the structure of your test bench, and then you have a graphical user interface that helps you navigate throughout all the files. So if you want to play with that, that's open source as well. A second open source one is quite simple. It's just a test bench generator I've been developing 6 years ago. It's just when you start with a test bench, you have to write a lot of not nice things just to wrap things up. So that's a Python script to generate VHDL test benches, system Verilog ones. Quite simple, but actually before the end of the summer, I hope there will be a new output over there. The idea of having kind of UVM test benches, but in VHDL. So it's the idea of having agents, sequencers, drivers, and so on. A bit like UVM, but just in VHDL for people who would like to play with that. So it's kind of a light UVVM, I would say, for people that would try something else. And finally, a last one, just because of the talks I saw here. So it's transaction-level modeling VHDL methodology, a big name for not that much, actually. It's just a bunch of packages for helping designing test benches. So I did that just yesterday evening, so that's an old code I've been developing and using in the institute. And the idea is that with that you can use objections. It's taken from UVM as well, to try to detect that everyone in the test bench is ready to stop. And heartbeats to detect inactivity, because that's an issue. Usually if everything is stuck, it's hard to detect that it goes bad. So that could help. So feel free to play with that. So back to formal verification. So the idea is really to prove that it works well, or that can be used in conjunction with simulation as well. I would suggest it's quite nice to use that to validate part of the system, maybe not an entire processor, as there was a question about this previously. It's quite nice on the control path. It's more difficult on the data path, for instance. And but actually, if we do it well, that's pretty nice, because you are thinking differently about your design. And the idea of verification is if you think differently about properties and what you should observe, it will help find bugs that you won't do if you just write a reference in VHDL that would maybe look a bit too much like your design. One issue is to think about all the properties, as we talked already about it. It's hard to think about everything that we should observe. It's not that easy to write good properties. It's very easy to write something that say, okay, it seems to work, but actually it's because the property is never fired, or never triggered, because something was never observed. Here, two tools. So I've been playing with Questa Formal thanks to the university program we have. So that's a commercial version. And we started with SymbiYosis 6 months ago, more or less. And so the difference is one is open source, which is better, the other one not. And one thing different is that Questa Formal is using model checking for doing that. So basically start from a reset and try to generate all the possible state from that reset. And with SymbiYosis and the tools that you have with that, there is model checking and also some prover, mathematical prover, and that could help in some setups. about the language, so you saw a bit of system Verilog assertions. Another way of doing this is using PSL, so it's property specification language. And that's actually a language that you can apply on VHDL, on Verilog, system Verilog, and so on. Because part of the language is just for this PSL, and else it's related to the flavor that you would have. So just to let you know what's happening with Forma, so that's the Wilson Research Group study published every 2 years. So we see that from 2012 up to 2022, so a lot of teams are now playing with Forma. And that's the way it seems to go. That's the trend, actually. And with this open source tool, that's getting easier for anyone to use it. In terms of languages, so we see that the system Verilog assertions are the more used. I guess it's because a lot of people are dealing with Verilog or system Verilog for design, and so it's easier to use system Verilog assertions. But if you are using VHDL, PSL would be a nice choice. Quite rapidly, PSL actually it allows to do different things. One is to use something called the linear temporal logic. So not only have assertions about A equals B, but really the idea of if I observe something for a certain amount of time, then I should observe something else, like another sequence. You can play with regular expressions as well. I will show you 2 or 3 examples on this. And actually, with system Verilog assertion, you can do more or less the same. There is just this conditional temporal logic. I won't explain exactly what it is right now, but it's a bit more complex, but it's part of the language, but not offered by the tools, so not really useful, actually. So both of them are quite the same. Some use cases, I've been using, it was with system Verilog assertion, counter, a simple FIFO. A FIFO with multiple channels and a calculator able to do some basic computations. And actually, that's why you have a lot of slides, because you have all these examples in system Verilog assertions at the end of the slides. You can download it. And if there are some questions, I can show you that later on. Just here to mention something quite interesting. We wrote a test bench for these 4 different designs, and you see how many lines we would need for assertions. So if you write well your properties, basically you can save some code and have a better verification of your design. So just about the context of the project we've been working on with SymbiYosis, that's an ESA mission called Comet Interceptor. That's a satellite that will go in space and wait for a comet to arrive, and when there is a comet, they will try to get as close as possible and do some experiments around the comet. And actually, the team has been working on the camera. And actually, this camera, there is an FPGA in the middle that has to deal with some analog inputs, HAL sensors, the heaters, and the motors, and get some commands, the telecommands, and send some telemetry data outside. And so that's kind of a big design. And this is obviously decomposed into many parts. So I will talk a bit about the LVDS receiver, which is where the commands are arriving in serial mode, a decoder to know where to send all the different commands, and a bit of the sender. Well, basically, we have to build some packets to be sent back as the telemetry. So just before going formal with that, what has been done by the team before we started playing formal, they used CocoTB. I think no one really talked about it these 3 days. That's a shame. For next year, maybe. And actually, CocoTB, that's the way of describing your test bench in Python, and just there is an easy way to interact with the VHDL. And then you enjoy Python and everything that is quite easy in the software world, and you can let software guy design the tests. And so there is a scenario generator, the driver, some checkers, and so on. What was quite interesting with that is that they have the hardware in the lab, a bit of wires, as you see, and actually they could use the same scenarios and checkers because they just had to change the monitors and the drivers to access the real hardware. So that's maybe something nice to look at, this CocoTB, because then you could reuse the same verification framework for the real hardware and the simulation. On that, so we had the opportunity to spend some time on Formal for this. So we used the open source tool, very easy to install, like 5 minutes, and you have this CAD suite ready, GTK wave to look at the waves, and that's all. And it was really nice because you don't need to install, like some years ago you had to install a lot of things by hand and it was kind of a nightmare. Now it's very easy. So we use PSL. A first flavor of this PSL, just I show you a counter with an enable and a load command, quite simple. And actually in PSL you could write a VUnit that you would put in another file. And actually you just define that you have a clock and then some properties. So we see a property, the first one says that if load is disabled and enable is 1, then on the next clock cycle, that's this operator here. On the next clock cycle, I should observe that the output value should be the previous output value plus 1. And that's all. With that, I'm checking that I'm incrementing correctly. If I'm not loading and the enable is off, then the value should stay stable. And if the load is 1, then the value should be the previous input data I would have. And so with that kind of code, I can give that to the checker, and it will say, OK, that's all right or not. Pretty easy for a simple counter, right? So on our design, what we've been dealing with, so 3 examples. The receiver, so we have a serial input with actually a kind of a clock, a slow clock, and on each edge of the clock, on this clock, we have to sample the data coming in. And for that, what can you do with such assertions? So I'm going to show some examples. So here, just one way of saying if this special clock is not stable for 8 times, I don't say how many clock cycles I have between these 8 times. We have an age on this. But just if it's not stable for 8 times, then within the next 5 clock cycles, I should observe a data valid. That's all. All right? And here, I'm aborting this assertion if there is a reset or if the data valid is on, because then we should start another instance of that assertion. So you see, it's just one line to say I have to wait 8 edges, and then within 5 clock cycles, I have to observe something. And if you think about how you would write VHDL code to check that would be quite a lot of nightmare or line of code to write. Another thing would be to check the data that we have at the end. We have an 8-bit data at the output, and so when data valid is on, then I should observe the real data on the outside. The issue here is how to build this real data, and so for that, here what we had to do, we had to write some VHDL. So we had to write a process just to build this 8-bit data. And then we can use an assertion to say that we want to observe that data. Depending on the on the tool, actually, if we would be using Questa Formal, there would be a way to build an assertion that would build the data in parallel. That's a bit more complex, and it's not the kind of thing that are supported by the open source tools right now. About an address decoder, we have here just to show you that we can build interesting things. So we are here building sequences. So you can define a sequence, And so here on the top, there is one sequence. I say on one clock cycle, I don't observe receiving, so receiving is 0. Then I have Rx valid data and the fact that this data corresponds to a certain value. And so that's a 2 clock cycles sequence. There are other sequences right here. And actually, then we can use these sequences to say, okay, when I observe this start transmission, then it means that I should observe start CRC, because I'm sending a CRC at the end, before this end byte goes to 1. And actually, with that, you can build some quite complex things as well, with quite few lines. About this address decoder, another example right here. For instance, I would just go on this one. Here, this assertion says that if the reset is falling, or if we observe the end transmission and then wait for 2 clock cycles, so 2 clock cycles after observing that, then I should be sure that this ACK TC is stable until we have these signals going to 1. And so it will check that this signal would be stable at 1 or 0 until that specific event. And then if you think about how to check that in VHDL, that would be less fun, I would say. Last one, data builder. So here we have a part that receives data, 496 bits, and that has to send it 16 by 16 and the CRC at the end. And so here just an example about the data. What we've been doing is that actually you could write a property that said if we are sending, so it means that there is some data going out, and we are not sending the first 32 bits are just A. If that's not the case, if you are not sending a CRC, then the frame data should be exactly the good part of the vector we have at the input. And actually, for doing this, we use this assume, saying, okay, we assume that this telemetry data is stable, because else the solver will try to put anything in that and it will go quite wrong. For that, we had to add a counter as well to be sure to go into the right part of the data. And that's kind of a limitation as well. Having as much as possible in the properties, but sometimes you need to write some helper code. One thing I wanted to mention, when SymbiYosis wins one set against Questa formal, back to the counter we had at the beginning. Actually, this counter, I just modified it with an internal counter that after a million clock cycles after a reset, just decrements instead of increments. So very easy to put that in VHDL, but quite hard to detect. Even if you're with a test bench, you will need a lot of clock cycles to detect that issue. And actually, Questa formal doesn't find it, because it would take too long actually to reach this million clock cycles. But the open source tools find it directly. I don't know exactly how they do that, but actually that's the good news. So congrats for the open source ones on this. So in conclusion, formal, I guess that's a good complementary approach to simulation. I would not suggest just to do pure formal, because it's going to be hard. Because actually, if you do a very good formal verification, you could say, okay, maybe if I have all the assertion properties of the system, you could give that to a tool that could generate your design. It would be great, no? Actually, there are 2 academic projects that try to do this, but you end up with quite of a difficult way of writing your properties, because it really shows that it's hard to think about all the properties that univocally define a design. But so, as a complementary approach to functional simulation, that's great. For me, that's a good way of thinking differently, because you saw these properties. I rapidly showed you, it's really a way of thinking about what should I observe depending on what I have as the input of the system, but not thinking in terms of how to design the thing or how to simulate that. So that's a good way of finding things. In another project, we found some issues we had because the test bench didn't end up in specific corner cases, so that was pretty good. It's pretty cool for control path, so I would suggest to at least use that to check that your protocol is well, and then for the data, maybe that's not the best way. But it means that you can write a test bench taking into account that all the control paths are good, so you don't need to check that. You can make the assumption that it works, and then you just focus on the data, which is quite good. As far as we tried, the open source tools with PSL are quite okay compared to the commercial ones. There is one issue that is not that good, is that in a property you can have some local variables. So you can save something if you observe something and then use that later on. And that's very good for a FIFO, for instance, for checking that. That's perfect. But actually we don't have it right now in the open source options. And last hint for the designers. If you want to play with formal, one of the issues is the search space. And if you have a lot of vectors and big arrays, it will be quite hard to really try to prove that your design is correct. And so I would strongly suggest to put as many generic parameters as possible in your design, even if you know that at the end you will have 32-bit data. Put your data width as a generic, because then you can use formal with just maybe 4 bits, and that would be enough to demonstrate that it works well, and then you can say, okay, it will be all right with 32 bits. And so do it as much as possible, and try to think about your design about reducing the search space as well. For instance, with this Comet camera, actually the data is sent quite slowly compared to the clock. And actually, if you have like 300 clock cycles for every bit to send, that's kind of a nightmare if you want to prove that it goes well. So if you have a generic that's say number of clock cycles for sending data, then you can prove it works well with a small value and then say, okay, it should be nice with more. And so that's the end of my talk. That's just the team. The first one are working on the project in itself and on the Python code. Alberto Dassati is a professor, colleague of mine, and the last two ones are the ones that really developed the PSL part on this. So thank you for the attention. Thank you very much.
Thank you very much for a very complete presentation.
Thank you very much for your presentation. Actually, I've got two questions. The first one is, you mentioned using OSS CAD and GTK waves. Why didn't you use a GTK wave embedded in OSS CAD? There was some kind of trouble, or?
No.
Not on your opinion?
No.
And the second one is more like you used UVVM and CocoTV.
Yeah.
And in your opinion, how does it match? What are the pros and cons between the two of them?
Good question. One thing, it depends on the team, I would say, because if in the team you have a lot of software engineers, for instance, working, maybe having a Python test bench could be quite nice, because then it's quite easy to develop the scenario. Actually, you need people, you need hardware engineers to really deal with the interaction with the Duve, because you need to know what is a clock. But then you can let people playing with Python scripts without this knowledge. But actually, in UVVM, you can more or less do the same. You have people that has to take some amount of time to play with the bus driver, the driver in itself. And then, as we saw, writing the test is quite easy. Okay. So, hard to say. One thing as well, maybe, is that UVVM, you have a methodology, so you have to follow the way you should go. And so that would be more, I would say, easier to share with others. With Python, we just have You just have CocoaDB and the way of interacting with the design. Then you can do any mess you want, and we are still missing a methodology around this.
Yeah, thanks.
There are two initiatives with UVM and Python. So there is PyUVM and UVM Python, two different teams that try to do the same as UVM in Python, but it's still not totally mature.
So you managed to have different people doing the design and the verification in your team?
That should be the idea. We have a small team, so it's usually not the case, but if you really want to check that everything goes well, you shouldn't have the same people writing the design and writing the test bench, because we usually agree with ourselves, so that's bad.
If you have only software engineers doing the verification.
Yeah.
I'm wondering whether you can recommend some ready-to-use or step-by-step examples that we can follow to more or less understand the SymbiYosis flow with.
Yeah, we have some examples. We just didn't put this as open source. But yeah, if you contact me, I can give you some hints on this. And I think that Nina did supply some material online.
Yeah, I can probably also Google them, but I don't know, maybe you have some good ones that you can recommend.
I don't really. So I have these examples of FIFO counters, some calculators.
Yeah, to answer on this, if you want to look at Colibri, which was my talk on Monday, we have formal verification for our components inside, and so they are in the source code. You can find them there. They are commented, so you can look at them.
So let's go for a coffee. Thank you so much once more. And we're
Thank you.
back.